How you doing? My name is Kevin Ford, and this is my presentation for Foundations of Computer Science for the first half of the semester. My presentation is going to focus on the textbook exercises that I've prepared, the ones that I've been doing at the end of the chapter, and I've done exercises for all of Chapter 1, and I've done a few in Chapter 2. What I'll be covering is deterministic finite automata, non-deterministic finite automata, how to prove that a language is not regular with the pumping property, and I also have some exercises here that talk about context-free grammars, and I don't know if I got down to push down automata, but so one of the first exercises that I've done was right here is exercise 1.3 in the textbook. So what this exercise is about is the textbook gives you the definition of a finite automata, the formal definition. It includes all of the states, the different characters in the alphabet, the transition function, the start state, and the accept states. So as you can see, this is the transition table. So as you can see over here I wrote a state diagram that follows this transition table here, and so the start state in this is Q3, and Q3 is also the accept state. There should be an arrow right here because this is the start state. Looks like I forgot that. So every time here you start at Q3, and then so if there's a U right here, you go to Q2, as you can see right here, and then if there's a D, you go to Q4. And then you kind of just read the graph like that. So each one of these on the left is a state. This is the state that you're presumably in, and this is the state that you're going to for each input, and all the arrows match. That one was really easy. And you know, as I went through these, they got easier. I got pretty good with these. This is exercise 1.4, and what exercise 1.4 has is these are all languages. These are all languages that can be represented by finite automata. Of course, the regular languages, because the definition of regular languages are languages that can be represented by finite automata, specifically deterministic finite automata. This one right here, so kind of the main point of this one right here is this is a language that has at least 3 A's and 2 B's. And how I started off doing this one, this is one that I found actually particularly interesting. Not so intuitive at first, but so this is a language that is like a compound language. It's a language that's made of 2 intersecting languages, and so I found it easiest to approach this by making state diagrams for one for each of the languages that are being compounded here. So I wrote the state diagram for a language that has just at least 3 A's, and then I wrote a state diagram here that is just at least 3 B's. Which made it easier because, as you can see in the next part here, there are a lot more states, and I found it very interesting here that you're taking each one of these right here, and you're kind of like making a grid out of it, because there's going to be so this language here has 4 states, and then this language here has 3 states. So there's going to be 4 times 3 total states in the compound language. So there's 12 states in total here. I didn't find this. at first I found myself drawing kind of winging it, kind of just drawing, trying to figure it out. I didn't until I read in the textbook that when you compound languages, that this is how it should look. And it makes a lot of sense as you go through it. You can see that there's a cage. So this would be the case where there's one A, and then if there's a B, maybe two B's. You still need two more A's. And if you start off with two A's, you have two A's. This is just a way to keep track of how many characters have been represented thus far. That one was very interesting. We'll go further. Let's see here. This is so going further. There are finite automata that can be represented by complements. So here, we need to represent a language that does not contain the substring a, b. Well, how I started off this one was writing down one that recognizes a, b, and then from there you just reverse each of the states, which is pretty intuitive. It makes sense. It's a lot, we learned that in our discrete structures class, kind of just how to do complements, and that made it a lot easier. You just switch the states, switch the accept states rather. Let's find a non-deterministic finite automata here that okay, here's one. So 1.7 is very similar to like 1.4, where you're just making state diagrams for the NFAs, and so